Here you go. You're not being recorded right now. Okay. Lab syllabus. Go. Lab number 3, Coulomb's law, is due tomorrow on the 27th. Down, and we are going to do, let's see, oh, it's lab number 6, not, wait a minute. We didn't, okay, I'm sorry, it's going to be this one here. We did lab number 4, right? Before, is that right? What they did, remind me that. So let's see, we did capacitors and dielectrics before, yeah. Okay. Parallel circuits is going to come later on. 5 and 6. Resistors and Ohm's law. Here you go. So you should upload, yeah, lab number 5. Lab report number 5. Resistors and Ohm's law. Let me save that as number 3. Let's see if we can do this parallel and series circuits today. Okay, although I don't want to do it right now because the lecture is still behind the lab, right? Let's see what happens. Let's see if you have time. If you have time, we do it. If you don't have time, we don't do it. Ohm's law. Okay, remember what I mentioned that to you before, right? There are 4 basic devices in electronics, in electricity and electronics. Basic elements. The capacitor that you are introduced to, and now the resistor. The resistor. Resistance is the electrical counterpart of the mechanical friction. Okay? So resistance slows down the motion of electrons. Not just electrons, but electric charges in general, Okay? So remember the difference. Remember the difference between conductors and electrical conductors and electrical insulators. What's the difference between them? In electrical conductors, the difference between electrical conductors and electrical insulators. Electrical conductors electrons move easily, freely, I can say freely, in the material, in the conducting material. Like metals, for instance, ionic solutions as well. Electrical insulators. In electrical insulators, electrons move. Electrons has difficulty in moving. Electrons have difficulty moving. Okay, that should be glass, wood, plastic, paper. So they stay concentrated on a given spot of the material. Now, okay, what does it mean about electrical resistance? What does it mean about electrical resistance? Well, it means, what does it mean about electrical resistance? Okay, it means that the resistance is lower in conductors and higher in insulators. That's what it means. If the electrons cannot move and resistance is what interferes with the motion of the electrons, of the electric charges, then it means that you have a very high resistance in insulators. Insulators have a very high resistance, okay? Insulators have a very, another way to write that down, right? Very high resistance, electrical resistance. Whereas conductors have a very low electrical resistance. So resistance is a way to quantify the ability of a material to let charge move inside it. So here you go. Resistance is a quantitative measure of motion of the charges in a material. Every material has a resistance. Keep that in mind, right? Every material has a resistance. You already know. Here you go. This, my metal key has less resistance than my water bottle, my plastic water bottle. Okay? Every material has an electrical resistance. Even the human body has electrical resistance. Blood has an electrical resistance. The skin has electrical resistance. The bones have an electrical resistance that can be measured, by the way. We can measure those electrical resistances. If I get my multimeter, I can measure the electrical resistance between the size of my hand. It's possible to do that. My multimeter allows me to measure resistance. Okay. However, we don't use any material that is available out there as a resistor in our circuit. We don't do that in our electrical circuit. What we do, we buy resistors from stores, electronic stores. Resistors that are industrial manufactured resistors, which are manufactured in mass, and we buy those things. Let me get some of the resistors for you to see here. I wonder I already showed that to you, right? Those things are dirty cheap. Because they are mass manufactured, they are dirty cheap. That's the beauty of the Industrial Revolution, right? That's one of the resistors that we have out there. Okay, they look just like that. If you go in the internet, you have all sorts of resistor size. You have large resistors, small resistors, and even microscopic resistors. Let's take a look at the. Let's go to Wikipedia, right? Resistor Wikipedia. Resistor Wikipedia. Here you go. Different resistors. That's the symbol of resistance. If you are writing, if you are drawing a electric circuit, you use either the symbol or the symbol. This one is the one that we use the most, the one at the top. And they have those color codes here to tell you what the value of the resistance. See that? You know, a bunch of resistors. Those things are very cheap. They cost like 1 cent. Okay? Theory of operation. Okay, we're gonna go through that. If you go to DigiKey, for instance, the website on DigiKey, you're going to see that they sell. Here you go, resistors. Now there are all sorts of resistors out there in the market. Here you go. Let's see, cheap resistor, surface mounted resistor, Resistors kit, resistors network, array, streamer, potential, ohmmeter. Let's see, sensor kits, optical. Let's try this one here. Let's see if they have. Yeah, that's a cheap resistor. It doesn't look like that resistor that you saw. It's different. See that? A little cheap. It has a. Let's take a look at its size. Let's see here. It's not this one I want to show you. Yeah, it's a little cheap. So there are all sorts of formats, but the most. Oh, see that? See the symbol of the resistor right here, and here's the symbol of the capacitor. See that? That's a circuit, capacitor and resistor. Here's the symbol of the battery. Capacitance is measured in farad, not Faraday, but farad. Resistance is measured in ohms. Okay, so let's see if I can see a I don't want those cheap resistors here. Let's see if we can get through-hole resistor. Let's try this one here. Let's see how it looks like. Yeah, okay. It's not exactly what you saw in those pictures, right? But it's similar. It's like a cylinder. Unfortunately, we do not have the color bands in this one. But the most resistors, they do have a color band. Let's see, chassis mounted resistor. Let's see, resistor kit. Let's look at this one here. Oh yeah, here you go. See that? And this resistor kit, price $101. This one is expensive. $91. How many? But they don't say how many comes here. But if you go, let's see, let's take a look at pricing, right? Pricing. Woo. Oh, that's a kit. It's not a single resistor. Oh, we're gonna want to go this way. Yeah, those resistors are kind of expensive. There must be 60 pieces. That's why. 60 pieces. $24, $25 divided by 60, and you get the price of those devices. Okay. So I'm not going to spend too much time, but let's go ahead and let's get into the. Let me see. Let's get into the lab, right? Let me see if I can find chassis. Maybe it's this one here. Yeah, they don't have the figures. No, that's not this one. If I cannot find it, just go resistor, trimmer, potentiometer, transistor, accessories, sensor kit, ceramic capacitor. No, that's not what it is. Specialized resistors, rotary potentium. Well, those resistors that you saw in Wikipedia is somewhere here in the DGQ website. Okay. One day I was looking into it, and so let's go get our handout. Resistors, capacitors, we did that before. Number 5. Okay. So it looks like we'll be, here's a note of mine. Okay, I put a note here. Virtual lab. Let's take a look at the Colorado website, University of Colorado website, PET simulation. Okay, here you go. That's how your resistor looks like, just like this one that I have. Several of them. Those are real life stuff. The objectives of this is to learn how to connect a ammeter to measure current. Let's see, Ohm's law. Yep. So previous lab, yeah, he talked about that previous virtual lab. We'll be using the same simulation kit that we used. Yeah, well, I don't remember using this simulation, did we? Let's see. Oh yeah, we did for the capacitor. Okay. Yeah, we did it, but it was not the same, exactly the same simulation. It was a different one. Okay, so we'll be using the same simulation kit. Therefore, it's important to remember what you were introduced about this kit. So let's go in there. Let's see here. This guy. Oh, all right. This we're going to put together a circuit with this guy. See, we just go ahead. See, we can have batteries here. Okay, and then we can mount a circuit. This guy. Here you go. If I want to put a resistor here, I put a oh, I also have a switch. Just to give you an example, it's not exactly what we want to do. Okay, the switch can be either open or closed. This switch here is exactly what we use to turn on and off the light in your room, okay? Light off, light on. Current off, current on. Electric charges moving in the circuit, electric charges stopped in the circuit. See the electric charges here? They put the negative charges right here. The battery provides the energy to get the charge moving. The battery is just like your engine of your car. That's what the battery is, the engine of your car. So let's introduce you, let's write down here about the resistors. Okay. Okay, I'm just repeating what I have here. Slow down the motion, the high electrical resistance, the lower. Let's take it out. Motion of electric charges referred as electric. Okay, motion of electric charges referred as electric current. That's what it's all about. If you put an electric charge to move, we have what we have, an electric current, just like a water current. I have already mentioned that at the top, so I can take it out. Remember about the electric conductors, allow electrical flow more easily. I wrote that down before, right, in real time. Resistance, oh, by the way, that's important. Resistance is measured in ohms. You can determine the resistance of a resistor in two different ways. By reading the color code imprinted in the resistor. Let me show you the Wikipedia again. Here you go. All those colors means a number, has a given representation, of a numeric representation, and you can find out how many ohms each of those resistors have because they have different colors. Either that, or you can use a multimeter. Let me get my multimeter. Here we go. Remember my box of toys. Oh, I don't need even to get that. Here you go. I'm going to stop sharing the screen so you can see the multimeter. Okay, that's a multimeter. Yeah, see the fake screen keep on interfering with the display of the multimeter. Okay. It's called multimeter because it can measure different things. It can measure, for instance, the energy in a battery in terms of voltage. It can measure the resistance of a resistor. Let me get that. Resistor. Oh yeah, right in here. Okay? So this is several instruments in a single one. Yeah, I gotta keep on moving this guy. The image of the multimeter is fading, right? Give me some feedback, please. Maybe I should turn off this fake background. Okay. So if I'm gonna measure the resistance of the resistor, I should turn it on. Here, I'm gonna measure the resistance of my hand. Let's do that. You can do that. Everybody can do that. This is very important stuff, okay, folks? If you're going to do any experiments in the lab, you have to know how to handle those things. Right now, my multimeter is indicating a number 1 in there. Doesn't mean 1 ohm. No, it doesn't mean 1 ohm. It means the resistance is very high. That's what this 1 means. Okay, and if I have my cables here, right? Plug it into the multimeter. Here's the probe. If I touch the metals, the probes to one another, what happens to the resistance? It becomes very low. Just 1 ohm in this case. Let me turn off this fake background. Can you see the multimeter there? Does it keep on disappearing from you? I don't like that. Give me some feedback, please. Disappear, right? So let me turn off the fake background so you can see it better. Yeah, sometimes you can see, sometimes you cannot see, right, Jasmine? You know, right now I see it here. Yeah, okay. Let me turn off the fake background just momentarily. Let's see. Choose virtual background. Let's see how I can. Let's see if I can turn it off. None. Okay, good. Now I have it. Okay, good. So here you go. Right now the probes are measuring the resistance between those 2 points, between the black and red point, and you have this funny number 1 in there. It's not exactly 1 ohm. This is not 1 ohm, okay? And notice also that I have set my dial to measure resistance, ohms. Okay, I can put in any scale I want. And it's still measuring, it's displaying that funny number 1. It's funny number 1. The number 1 is to the left. And this number 1 here in this multimeter means a very high resistance. That's what it means. Also, some multimeters display like overload. If I touch one probe to the other one, here you go, right now, what's going to happen? The resistance is going to go to 0. See that? The resistance is going to go to 0. Because I am in a scale that's not very sensitive, it's displaying 0. But if I go to a very sensitive scale, extremely sensitive scale, the most sensitive scale that I have, we see that it displays not 0, but something still small, 0.6 ohms. Okay? And now I can start measuring the resistance of my hand, for instance. That's a nice exercise that we do in the lab. Go, this guy is upside down. Here you go. I'm gonna get my camera, I'm gonna put it elsewhere. Bring it here. Here you go. Multimeter. Oh, what's going on here? Yeah, okay. Better, I don't have to keep on holding. Here you go. Right now my probe is measuring the resistance between those 2 points here in the air. Air has a very high resistance. If I touch one point, one probe to another, it's measuring the resistance of this metal, those metallic probes. Okay? And the resistance goes very low. I go ahead and measure the resistance. Don't forget, I change the multimeter to measure resistance. Ohm here. If I go and get my keys, here you go. Right in here. I'm going to measure the resistance between this point and this other point in my key. Right in here. Here you go. This point and this other point. Ah, yeah, see, because it's a metal, the resistance of my key is very low. 0.9 ohms. But if I measure the resistance of my pen from this point to this point, what we get? You get a very high resistance. I'm going to change the scale again. Here you go. Let's see. I'm going to put the least sensitive scale that I can. Okay? Yeah. The resistance of this pen is more than 20 million ohm. Okay? Probe closer. I'm going to keep them closer and closer. Let's see if it changes. It doesn't change at all. Okay, what about this resistor, this real life resistor that I have here? Let's measure the resistance of this resistor that I have here. I wrote that down. It's not. Oh yeah, it's supposed to be 10,000 ohms. Let's see what we get for this resistor. It's giving me, displaying me 0. So I have to change the scale. Let me change the scale. 20,000. Yeah. See, I'm getting 9.8 thousand. 9,800 ohms for this single resist, very close to 10,000. 20% difference, right? 9.7, 9.8 to 10 is 20% difference, which is, by the way, is a big difference. Let's see this other one. Yeah, 9,730. Okay, that's how you measure those things in real life. Oh, let's measure the resistance of my hand, right? Hopefully, I'm not gonna get hurt here. Here you go. You know, I'm putting my probe right here at the front of my hand and at the back of my hand. The resistance between those 2 points is more than 20,000 ohms. Let's see if it's going to be less than 20 million ohms. Oh yeah, it looks like it's less than 20 million ohms. See that? The body has some conducting properties, but it still has a very high resistance. I'm getting 3 million ohms, and it's slow to measure. You still have a time lag. It's keep on changing. 3,800,000, 3,900,000. So the human body is not a reliable resistor. Okay, now it's going down, fluctuating around 3 million. Oh, fluctuating around 3 million. Let's see my finger. I don't think it's going to change anything. Oh, my finger, because of the nail. The nail is, let's see, what about here? Yeah, the fingers are a little similar to the hand. 3 million ohms. Okay, but again, because the human body is not a reliable resistor, its resistance keep on changing. We have blood moving through the body, right? And that affects the resistance. So that's what I have to show that to you. 137, and I'm gonna put my camera back where it was. By the way, this part I was not able to record. Keep in mind, I was not able to record in my screen capture software, okay? Because the screen capture software is not talking to my camera. There must be some problem between Zoom and my screen capture software that doesn't allow. There must be a conflict. It doesn't allow it to capture, to use the camera simultaneously with the Zoom. Let's take a look. I'm going to start sharing the screen again. Okay, here you go. Resistance is measured in ohms. Remember, the electric motion of electric charges is referred as electric current, just like in water current. Electric current is measured in coulombs per second, right? Velocity is meter per second, right? electric current, which is a measure of the velocity of the electric charge, is coulombs per second. It's coulombs per second. And this unit we represent by the letter A, that means ampere. Okay, resistance is measured in ohms. One more thing that you have to know, one more thing that we'll be covering in the lecture, you have to know is the voltage of a source. Okay, voltage is a measure of the energy provided by a circuit, provided by a battery, for instance, to a circuit. So voltage is what? Voltage is joules per coulomb, unit of energy per unit of electric charge. Okay, volts equal to V. Go. Go. Ampere. And then that's what we study first before we go talk about resistance. Then we have resistance, the unit of resistance, which is the ohms, represented by the capital omega letter. There is a relationship between volts and amperes. Okay, so what's the relationship? The relationship is volts is equal to resistance times current. You know, in terms of units, what we have that volts is equal to ohms times ampere. Pick up like that. So if you want to know how ohms related to voltage and the other things, right, you have to solve this equation here. I can go even further. If you're not familiar with those units, I can here write those units in familiar format. I'm going to use my software here. I want to finish that before we go in a break. Bear with me. Here you go. Let's put my ohms. I don't have okay, I gotta go elsewhere. I don't have ohms here in this pane. Let me get here ohms. Greek letters. Here you go. Ohms, last letter of the Greek alphabet. It's volts divided by amperes, capital A. And then let's not forget joule. Volts is joules per coulomb divided by, here you go, divided by coulomb per second, right? So we have this complicated unit that ends up being joules second, coulomb square. That's what ohms is all about, joules seconds, coulomb square. But if you want something like that, it's just volts per amps. Okay, what you see here is what we call Ohm's law. Ohm's law. It's not a law, so put it between. It's not an actual law, but it's the result of something else. So put it between quotes. People call it law just to, just to be nice to that guy that discovered it first. So you can measure resistance two different ways, by reading its color code or by measuring the resistance using a multimeter. We did both of them. The color code, you have to find out the number of each color. Okay, so why do we have the color code? Okay, in the past, when multimeters were expensive, people would use the color code to find out the resistance. Today, with cheap multimeters, you can buy one by $10. It's far more convenient to measure the resistance using the multimeters. Okay, here goes step by step. Right side the multimeter with the resistance, touch the probe to the end of the resistor to measure the resistance with the color code. Use the color of each band imprinted in the resistor to determine its resistance. Okay, so you can read that later on. I'm not going to go through that. So let's take attendance now. That's not the one I want. Lab. Today is the 26th. Bella, are you there, Bella?
Here.
Okay, good. Annabella.
Here.
Let me get here the chat. Good. Next, Sarah. Are you there, Sarah?
I'm here.
Carly?
Here.
Next is Mahedi Hassan.
Here.
One more, Wesley.
Here.
Next, Ada.
Here.
Jordan.
Here.
Donica.
Here.
Shagar Nurali.
Here.
Daniela Rodas.
Here.
Dior Simons.
Here.
Shreya.
Here.
Peter. Peter
Here.
here. Okay. Ana Ponce.
Here.
Kaylee. Are you there, Kaylee? Okay, she left. Okay. Cannot give attendance to her. Alisa.
Here.
Next, Jasmine Tobar.
Here.
Okay, 17. We have 17. And let me put here early. And now is 147. Lab notes. I want to skip that. Definition of average. Here you go. I covered that. Here you go. That's Ohm's law. I mentioned there at the top. So break. Let's do like 150 to 205. Okay. So I see you in 15 minutes. A little bit more than 15 minutes because 147. I see you soon. Stop sharing. mais vezes tem mais tem mais So let's start sharing here the screen and let's go to the handouts. There's resistors and Ohm, right? Ohm's law. So we have here the simulation. Let's see how he wants us to do. Ohm's law. Ohm's law is that V equal to Ri. Equation that you saw. Let me share the, here you go. V equal to Ri. This is a measure of the energy provided to the circuit. In a very good way, I want to show that to you how you can interpret this delta V here, right? Either delta V or V, either way. So here you go. Using a battery, a switch, and the color-coded resistor, build the circuit shown in figure 10.7. Okay? So here you go. I start doing that. Battery, switch, and resistor. Which resistor does you want? Okay, we get there. Here you go, wire. I'm going to keep the switch open. And I'm going to show to you how does it, something like that looks like in real life, okay? So get any circuit, any resistor that you have there. Let's do exactly the way it's there in the drawing. Here you go. We have far, fancier computer programs, simulations like that that show that you use for a circuit. Okay, so here you go. Wire. Here you go. He wants a wire here. Let's do according to what's in there. Put any resistor for now, and then you will be able to change the resistance of the resistor. Close the circuit. The circuit's still not closed because the switch here is open. Okay, see the switch open here? Using a battery, a switch, and the color-coded resistor. Build the circuit shown in this figure. Set the source voltage, the potential difference to Vs equal to 0. Yeah, they put that Vs equal to 0. I wonder why. Let's see. Remember to change the source. Remember, to change the source voltage, you need to click. Okay, so let's go there. Right now, double click. See, right now it has 9 volts here. It had to put 0 volts. It's strange. Let me make sure that I didn't change anything in the original handout. Okay, yeah, he put 0 volts here. Maybe he's gonna change that later on. Let's see what happens. Okay, so you double click here, and you can change the voltage. Okay, I'm gonna explain to you what this voltage is all about. Okay, here you go. Set the resistance of the resistor to 47 ohms. That's a relatively low resistance. So you double click here, 47. Yeah. Did you notice that the colors change, right? Here you go. See, the colors keep on changing. Each of those colors means a number. Okay, signifies a number. But he wants 47. Okay, like that. How do you connect a multimeter to measure the voltage across the resistor? Okay, I'm gonna show you how to do that. How do you connect a millimeter? What's the difference between a millimeter and you? If you have answer, I'm gonna show you how to connect all the stuff. Oh yeah, set the okay. Initially set the voltage to 0. But then later on he asks you to set it to half volt. Okay? So what's the difference between? Okay, so let me show you in real life how we. I want to be able to do that because my. Let's see here. Let me see if I can. That's an unfortunate. I'm not gonna do that in real life. Okay. I can't share my video with you here with Zoom. But the voltmeter. How do we measure the voltage across the resistor? Okay, it's very important, okay? Voltage, I'm gonna write that down here for you. Lecture notes, that's something that you have to memorize, okay? Voltage is measured by connecting the multimeter in parallel with the element of the circuit, okay? Current is all the way around. You have to memorize that, okay? Current is measured by connecting the multimeter in series with the element of the circuit. See the difference? One thing is connected in one way. The other is connected in another. And I'm going to show you how to do that. We are going to get the voltmeter. Here you go, voltmeter right in here. Go back to the, how do you connect the voltmeter to measure the voltage across the resistor, okay? Here's my resistor. So I'm gonna put the voltmeter here. You connect, here you go, at the ends of the resistor, okay? We're measuring the voltage right now. Because the circuit is open and the battery still is set at 0 volts, there is no drop in voltage whatsoever. There is no drop in what? In energy. That's what this voltage is all about. There is no energy being furnished because the circuit is open, and because there is no energy being furnished, then there is no loss in energy here across the resistor. That's how you should interpret that. And you connect that in parallel. That's an important thing about measuring voltage in your circuit. Let's go back to, here we go, to our, how do you connect the ammeter to measure the current passing through the resistor? Okay, the ammeter is different, just like I said. You have to connect it in series. And how it looks like in series is one after the other. Do you see that the voltmeter is in parallel? The two ends here is connected to the resistor. In the case of the ammeter, you don't do that. In the case of the ammeter, let me get that. Here we go. Like that. Here you go. Okay, gotta be careful, okay? So if I take it out, this probe out of the end of the resistor, you're gonna get a question mark. But if I put it back, you get 0 volts. See, the ammeter is in series with the circuit. One item after another. One item after another, that's ammeter in series. Connection in series. There you go. So that's the answer for that question in there. What's the difference between an ammeter and a voltmeter in terms of how you put it in the circuit? So you already know the difference. One goes in parallel, the other goes in series. If you answer the questions above correctly, connect the ammeter and the voltmeter according. I already did that for you, right? Now turn the switch on. Check the box for conventional values and the battery symbol. Let's do that. Here you go. Switch. Oh, yeah. Here you go. You got it. Conventional. What's that conventional? Let's see here. Now turn the switch. Check the box for conventional values and the battery symbol. After performing this step, for example, what I see on the screen showing figure 10.8. Conventional values. Here you go. Oh, conventional. Here you go. That's what he means. Show the current. The current can be shown either in a conventional way or in terms of the motion of the electrons, okay? One is just the opposite of the other. Values. Okay, now we have the values here. 0 volt. Do you see here the resistance of the switch? Because the switch is open, the resistor is infinite ohms. Very large ohms. If I close, the resistance becomes 0. Okay? Open it. We have a resistance due to the air that's between those two ends. Okay, so let's go. Next step. Set the source voltage of the battery to 0.5 volts. When we set the source voltage, I'm going to show you exactly what this voltage is all about. Let's put it there. You go. Click it, right? Half only. Oh, too much. Let's see if we can type it. Oh, you got it here. Here you go. 0.1, 0.2, 0.3, 0.4, 0.5. Okay? And now we have to close the switch. Read the current I through the, okay, close the switch now. Here you go. Now you see the current flowing through the circuit. See the arrows here? See the arrows here? Here's the negative side of the battery. Here's the positive side of the battery. So that's what we call the conventional direction of the current. So basically what you have to visualize that, you know, what you have to visualize in the conventional way, the conventional way shows the motion of the charges if the charges were positive. That's what the conventional direction of the current is all about. I'm going to put that in the notes, okay? Lab notes. In the conventional way, the motion of the charges shown is the one that would be in case the charges were positive. Okay? In case that the charges that were moving were positive. And there is a reason for that. Okay, but in reality, that's not the charge, not the positive charges that I move. Do you see that sometimes the arrows move, right? So here you go. In reality, you know, when something like that when circuits start to be created before, people thought that current in a circuit was due to positive charges. That's what they thought initially. Later on, we discovered that was not due to positive charges. Later on, we discovered that was due to motion of electrons. Okay? And the motion of the electrons is opposite to the motion of the positive charges. Negative charges move in a direction opposite to the positive charges in a circuit. Right now, we cannot see the electrons moving because the voltage is too low. But if I increase the voltage, I'm going to show you an animation. Here you go. Now you see it. See that? The voltage is so low at 0.5 volts that we barely see the charges moving. Okay, now let's put the conventional. I'm going to show you the conventional. See that? Here you go. If if it was the positive charges that contributed to the current, the positive charges would move in this clockwise direction. Okay? But in reality, that's what we thought initially. That's what scientists thought initially, back in the 1700s and the 1800s. Later on, we discovered that the current was due to the motion of electrons instead. Okay, which moves, in this direction, opposite to that of the positive charges. Okay, so let's put that in here in the notes. In the conventional way, the motion charge shown is the one that would be in case the charges were positive. The current were due to the motion of positive charges. In reality, this is not the case. This is not the case. The current is due to the motion of electrons, which move in an opposite direction. Keep that in mind so you don't become confused. In the opposite direction of that of a positive charge. Okay? So every circuit that I'm going to see out there shows the direction of motion of the positive charges, not the negative charges, like that. Okay? And if I decrease the voltage of my battery, look what that happens to the motion of my charges, decrease. And look here at the current. See that the current? I'm going to increase the voltage. Here you go. I increase the voltage, charges move faster, and the current increases. I decrease the voltage, charge moves slower, and the current decreases. The amount of charge per unit of second going through the ammeter is lower. Okay, going back to half, we're gonna have such a low voltage that we'll barely see any motion of the charge. See that? Let's go back to half volts. Here you go, 3.8, 3.7. If 3.4, see, it's very slow. You can barely see it. If 3.4 is you can barely see, imagine back to 1.5. Here you go, 2, 1.5. Here you go, 5.5. It looks like it's static, right? But in reality, there is a motion here. There's some motion going on here. It's just that you cannot see because the charges are moving very slowly. And look at the current. The current is 0.011. The voltage, okay, showing the question mark because I don't have a proper contact here. But now I have. The battery is producing half volts. The battery is inputting half joules per coulomb to the circuit. Okay, that's the energy that the battery is providing, and the resistor is extracting this voltage. It's extracting half volts. That's how you should interpret the voltage. Okay, because the resistance is like the electrical counterpart of the mechanical friction. The mechanical friction is removing the equivalent energy provided by the battery. That's how you should interpret it. Okay? Notice what happened if I switch the probes here, you get a negative voltage. Okay? Why is that? Because the negative here is facing the positive of the battery. You can put your probe right in here as well. Here you go, in the battery, see? The multimeter is going to measure half volt. So let's put it back here. So, any questions about that? Let's see if let's put my chat window. right in here. Let me see if everybody's following. Going to the here you go. Bella, are you there, Bella? Do you get the
Yeah.
okay. Do you get to see the current moving there, Bella? Just like I showed to you all?
Yes.
Okay, good. So let's see who else. Annabella,
Yes.
any problems with the simulation?
Yeah, I can see.
Okay. Let's see. We have 17 students there. Okay. Sarah?
I can see.
Okay, no problem. Are you working there with your simulation? Carly?
Yes.
No problem. Mahedi?
Yeah, I'm good.
Good. Wesley? Are you in good shape, Wesley? I can't hear you. Okay, good. Thank you. Ada?
Yes.
Okay, thank you. Jordan?
Yes.
Donica?
Yes.
Shagar?
Yeah, I'm good.
Okay, Daniela?
Yes.
Okay, Dior?
I'm good.
Good. Do you have any problems with the simulation there, Dior?
No, I'm good.
Okay, good. Shreya?
I'm good too.
Okay, Peter?
Yeah, I'm good.
Okay, Ana Ponce?
I'm good.
Okay, Kaylee, she left, right? Okay, Alisa?
Yeah.
Okay, good. And Jasmine?
Yes.
Good. Okay. So let's go ahead and get the next step here in our handout. Corrected. So set the source voltage to have volt, read the current I through, and the potential difference across the resistor from the ammeter. You must read a non-zero, okay, non-zero value. Non-zero value. Record your values in the appropriate columns. Okay, so let's do it. Let's do our table. Let's go to our Excel spreadsheet, right? I'm going to create a new spreadsheet here. Go. Rename, and that's going to be number 5, right? Lab 5. Resistance. We'll put Ohm's law. Ohm's law. Here you go. I'm gonna zoom in here for you. Right, we're going to put, what you're going to do, you're going to put current in the left side. Yeah, current. Current is usually represented by the letter capital A, and you put the unit amps. And the volts, okay, represented by the letter V, and the unit V as well, voltage. How many do we want? 1, 2, 3, 4, 5, 6, 7. Okay, well, I'm gonna make 7 measurements. So 1, 2, 3, 4, 5, 6, 7, right in here. Seek borders like that. Here you go. Centralize. We start with half volts. Here you go. And then what did you get there? Do you remember what we got there? 0.011, right? Yeah, 0.011 amperes. 1, 2, 3, that's 11 milliamperes. That's a reasonable current in a circuit. That's what you see in most circuits out there, in your cell phone, LEDs, 11 milliamps. It doesn't kill you, you know. You can hardly feel it. Now, what else? What voltage does he want us to increase? He didn't say, right? Record, set your voltage, the battery to the half volt, blah, blah, blah. You must, across the resistor, record your values in the appropriate color. He didn't say what values. Oh, yeah, he said here, increase the voltage by another half volt until you reach 3.5. Here you go. Let's go. No, wait a minute. 1, 1.5, 2, 2.5, 3, 3.5. This way. Format cell, just one. I'm gonna put only one decimal place there, so it looks nice. I'm gonna shrink this table a little bit so we get as much space as we can, and then we're gonna increase the voltage. That's what we do in the lab, okay? When I'm doing experiments there in the lab with my students, real experiments, I do exactly that. So it is a realistic simulation, the one we are doing here. We don't use a battery, of course. We use something else that's similar to a battery. We use a power supply. Here you go. Let's increase, which is a variable battery. Do you see what happened to the current here? Let's see if I can get, yeah, tap element. 1 volt now, 0.02. What happens to the voltage? The voltage didn't change. See that? There's a reason for that. I'm going to cover that when we get into electrical circuits in the lecture. So let's go ahead and 0.02. It increased, right? 0.11 to 0.02, almost twice. It's not exactly twice, but it's almost twice. You increase the voltage by twice, the current is increased by twice. Now let's go 1.5. Okay, 0.03. 0.03. See? Almost 3 times than what we had before. Not this one. Not this one. It's this one here. 2. See, the voltage increased accordingly. Okay, the same voltage as here. Went to 0.4. 0.04, right? 0.04, not 0.4, 0.04. 2.5. Okay, in real life you'd get more decimal places here. But that doesn't look, let me see, advanced, maybe we can, no. We cannot increase the decimal places here in the current, in the multimeter, in the ammeter. Ammeter to measure current, voltmeter to measure voltage. Okay, now we start to see the arrows moving here. Did I get 0.05? Not yet. Next, 3 volts. Here you go. Click it. 3 volts, 0.06. 0.06. 6 times the voltage, almost 6 times the current. And then the last one, 3.5. Here you go, 0.07. 0.07. So let me repeat again what we have here. The battery is a source of energy. It's just like your engine of your car. Okay, it is providing energy to this circuit. Okay, this input energy, the resistor burn the energy out. So much that whenever you have a resistor here in the circuit, the resistor becomes warmer, by the way. Just like object, whenever you add friction to them, right? You provide friction to them, they become warm. Your hand warms up, right? When you're rubbing your hand against the other one, your hand warms up. The same thing happens here to your resistor. Anything else? And then what we gotta do? Now we gotta press plot the graph, right? Close that. Okay, here you go. Ohm's law relates to the voltage across the resistor and the current. Right? I is delta V over R. Using Excel, make a graph. Well, let me see. You know, this guy here. The correct way would be VR versus I. That's how it's supposed to be. Okay? I'm gonna put that. Okay? What goes in what shows up first is what? You know what goes in the vertical, in the y-axis. So let me double strike that. Okay, good. So let's plot it. VR in the y-axis, okay? And I in the x-axis. VR in the y-axis, I in the x-axis, Here you go. Let's plot it now. Here you go. Insert chart graph straight line. Let me write it down, your Ohm's law again. Let's write down the Ohm's law. Lab notes. Here you go. That's Ohm's law. I'm going to write it down in a different way. I'm going to write it down as V sub R without the delta V there. V sub R. Okay. If V changes and R is kept constant, I didn't change the resistance, the I must change as well. And we must have a straight line with a slope given by the resistor. We do that in real life, in the lab. So let's go ahead. Don't forget to put, all the chart elements, axis title, right? I'm not gonna do that. Here you go. This one here, axis title, primary vertical, blah blah blah, right? I put the unit, V put the unit. And what else you have to do? You gotta put the trend line. Linear, display equation on chart, display R square on chart. Here you go. Do you note, see here the slope what it is? It's not exactly 47. It's 50. We get a percentage, supposed to be 47. We are getting 3 units out of almost 50. So that would be what? 4 units out of 50 is 10%. A little bit less than 10% is 7% and a half difference. 7% and a half, maybe 8%. That's the percentage difference that we are getting for this data. Let's move forward. 245. Okay, we have more time to go ahead here. Resistance of the resistor. Just put what I got in there, 50 ohms. I'm getting 50 ohms. It's supposed to be 47. There is a difference in there. Yeah, there is a difference in there. If you want to get the exact value, let's get the exact percentage difference. I don't know exactly, but I estimate that's going to be 7 to 8%. Okay, here you go. Ohm's law. Ohm's law. What's going on here? Okay, good. Well, I'm getting that the experimental value of the resistance is 47 ohms. You know, no, not the experimental, the theoretical. We call that the theoretical. The experimental that I'm getting is 50.5, right? Experimental that I'm getting there. No, not here, here. 50.532. Let's put just 50.5. 50.5. I want to get the percentage difference, PC difference. What do? You get the magnitude of the R theoretical minus, the R experimental divided by R theoretical. Oh, no. Okay, I gotta get that right here. Divided by R theoretical. Multiply it by 100. So substitute those values. Calculate all of that. You go. Expand, calculate. Let's see what's going on here. What a shame, huh? It's not doing my calculations. There's something wrong. I think I know what is. Nope. Let's see. Expand. Let's see. Yeah, it looks like he's doing something. PC difference. Let me see what's going on here. I know it's a little trick of the software. Bear with me. Notebook, get info. It's a variable, that's good. What about this one? Notebook, get info. It's a function, see, that's the problem. So I gotta change this guy to a variable. Yeah, it doesn't let me do it. Okay, so I have to give it another name, EX. I'm gonna put EX only. He's treating this lowercase, this subscript as a function. Experimental. Okay, now we have everything. Let's see. Dominica is coming. Let's calculate that now. Calculate it. Yeah. No, let's see what's going on here. I know what's going on. I'm gonna put everybody under the same. Okay, now you got it. A little tricky here. Okay, you gotta know what you're doing. Right, calculate this guy here. We get, let's see, what's the percentage difference? Calculate 7.4%, just like I told you. Okay, almost 7.5%. It's a small percentage difference, is acceptable. Anything below 10% is acceptable. Let's go for another. Here you go. Find the percentage difference. Make a sketch of your graph. Oh, that's it. Results and conclusion. That's a very quick experiment. Okay, that's a very quick experiment. That's, I'm not going to term, let's see, 250 right now. Let's get another break, okay? And we have 17 students here. No, we have 16 students here. What happened to the other student? Let me see what happened to, who is missing here? 17. Oh yeah, we have 16 now. Someone has logged off. Let's see. Bella, are you there, Bella?
I'm here.
Okay. One more. Annabella.
Yeah.
Okay. Next, Sarah. Are you there, Sarah? Okay. I'm gonna put it here. No answer. Are you there, Sarah? I don't hear you. I don't see you. No answer. Next, Carly is here, right, Carly?
Yes, I'm here.
Okay, Mahedi.
Here.
Okay. Next is Wesley Motley.
Yeah, I'm here.
Oops. Ada.
Here.
Jordan Tuttle.
Here.
Okay. Donica Ochoa. Okay, good. Thank you, Donica. Shagar Nurali.
Here.
Good. Daniela Rodas.
Here.
Dior Simons.
Here.
Shreya Sridhar.
Here.
Peter Gergs. Peter, I see you here. Okay, so, but no answer, I don't hear any answer from Peter. Anna?
Here.
Okay. Alisa Quintero?
Here.
Good. Jasmine Tobar?
Here.
Okay. Okay, 2:53 right now. Let's have another break right now. What I want to do, I don't think I'm gonna do another lab today, but I'm gonna use the remaining of the time for a lecture, okay? So you don't fall too behind the lecture and the lab. Let's do it this way. And I will record the lecture as well. I will post the lecture there. Just I'm gonna post the lab. I'm gonna keep two separate files. And any questions? Okay, and here you go. Let's see, lab syllabus, right? Here you go. Yeah, let's do the parallel and series circuit. That's the syllabus. Yeah, lab syllabus. Let's do the parallel and series circuits next time. And I'll rather do two labs in the same day when everybody's present. Okay, so they don't miss two labs. That's why I'm doing that. Magnetic field has to be postponed to the next one, right? Here you go. Resistors 1, 2, 3, 4, 5, 6, 7. Remember, we have to have two meetings in which we do two labs. Maybe we do that for the final ones. Maybe we should do that. The ones that don't have a lab, right? So 5, 6, 7, 8. Okay, which one? And then we have 9, 8, 9, 10, 11, 12. Resistors, let's see, there should be 6, 7 here. There should be 8, 8, 9. I will let you know which one we do not have a lab report. It's going to be either magnetic field or the Faraday law of induction. Parallel and series circuits is 2:56. Okay, let's have our break now. 15-minute break. And we come back at 3:10. Lab notes break from 2:55 to 3:10. Okay, so I see you soon.